Hey you, yes you, just relax. You could grab a book and a pen if you like and prepare to conquer this concept completely, because in this video I'm going to show you how you can solve any problem in Gauss's law, particularly applications, with 3 easy steps. Before that, let's quickly run through some basics. Electric flux is equal to the closed integral of the electric field vector times the A vector. And Gauss's law, electric flux is equal to the charge enclosed divided by epsilon naught. So we know flux is this, and that same flux is also this. That means the closed integral of E times the A vector is equal to the charge enclosed divided by epsilon naught. Now there are particular charge symmetries that make the electric field constant. When we have objects with those symmetries, this expression becomes useful because we can bring out the constant E from the integral and find the electric field. So like this, E times the integral of the A, which is A. So EA is equal to the charge enclosed over epsilon naught, and the electric field is equal to charge enclosed over A epsilon naught. This is the whole point of Gauss's law, and so this is the magic formula we are going to use to tackle all the problems. Phew. Now back to business. You'll encounter basically 3 kinds of problems, and the rest are just mutants. So here's how you can do it in 3 simple steps. The first kind is electric field near an infinite line of charge. Let's pretend it's not weird at all that we're finding the electric field of an unending line of charge, because trust me, you've done this before. Remember when you were doing lenses and you found the image distance of an object at infinity? Wow. However, what infinite means in this case is that the line of charge is very long compared to the distance at which you want to find the electric field. Step 1. Draw a suitable Gaussian surface around the point at which you want to find the electric field. Let's say it's at point P at distance r from the line of charge. Remember, there are 3 Gaussian surfaces: cylindrical, spherical, and planar. So which one do we use? Usually, if the object has length like this, use cylindrical. I'll be drawing the Gaussian surfaces in dotted lines because they actually aren't real. Step 2. Write down the magic formula. Step 3. Substitute your variables, keeping in mind 2 things. You'll come across a new term called charge density, because we'll be dealing with continuous charge distributions, not just point charges. And 2. Don't forget that the area is a vector and it needs to be in a particular direction. The normals of the area need to be parallel to the electric field. Resolving it accordingly would give EA cos theta. With that in mind, let's substitute. Let's say the line of charge has linear charge density lambda, and the charge density is the charge per unit length, so the formula is total Q over total length. Therefore, charge enclosed by our Gaussian surface specifically would be the charge per unit length, that is the linear charge density, times the length of the Gaussian surface, which is equal to lambda L. Epsilon naught is constant. What is our area? Remember, direction is key. The normals of the 2 circular bases are perpendicular to the plane of the electric field. So theta is 90, because 90 is 0, and those areas do not contribute to the flux. However, the normals of the curved surface at each point is parallel to the radial electric field. So theta is 0, because 0 is 1. So our flux is E times the area of the curved surface. The area of the curved surface is 2 pi RL. Therefore, E times 2 pi RL is equal to lambda L, substituting Q, over epsilon naught. E is equal to lambda L over 2 pi RL epsilon naught. The L's cancel out. E is equal to lambda over 2 pi R epsilon naught. If we had real values, you just plug them in to get your electric field. To save time, you could memorize this formula for any infinite line of charge question. But you know those days when you're having a test and you just can't remember the formula? This method is a lifesaver. Let's try an example very quickly. Lightning strikes the ground. Consider a brief period during which the lightning strikes, and assume that in that short time, all the charges are uniformly distributed in a long thin line of charge density 4 times 10 raised to the power of minus 8 coulomb per meter. If someone is standing 0.5 meters from it, what is the electric field at that point, and is it safe? Okay. So if this is our lightning, which is considered as an infinitely long charge. Step 1. Draw your cylindrical Gaussian surface where you want to calculate the field at 0.5 meters from the charge. Step 2. EA is equal to charge enclosed over epsilon naught. From what we've previously done, you know that the area is 2 pi RL, which is 2 pi times 0.5 L, and charge enclosed is lambda times the length, which is 3 times 10 raised to the power minus 3L. So E times 2 pi times 0.5 L is equal to 3 times 10 raised to the power minus 3L over epsilon naught. The L's cancel out, so the field does not even depend on the length. E is equal to 3 times 10 raised to the power minus 3 over 2 pi times 0.5 times 8.85 times 10 raised to the power minus 12. E is equal to 1.1 times 10 raised to the power 8 Newton per coulomb. That's a large electric field intensity, so potential difference will be large. So current is going to flow probably through the surface of the ground to the person, and that's not safe at all. The second kind of question is electric field near an infinite plane of charge. Step 1. I'll draw a cylindrical Gaussian surface at the point I want to find the electric field. Cylindrical because it has length. Step 2. EA is equal to charge enclosed over epsilon naught. Step 3. Substitute Q and area, remembering the rules. The charge density, in this case, surface charge density, because we are dealing with area now, is sigma, which is equal to the charge over the area. Therefore, charge is sigma times A. So what area are we going to use for the flux? We have 3, 2 circular and 1 curved, but we are going to use only the 2 circular because their normals are parallel to the plane of the electric field, whereas the normal of the curved surface is perpendicular and does not contribute to the flux. The flux through the 2 circular bases is going to be EA plus EA equal to sigma A over epsilon naught. 2EA is equal to sigma A over epsilon naught. The A's cancel out. 2E is equal to sigma over epsilon naught. E is equal to sigma over 2 epsilon naught. If this video has been helpful to you so far, consider liking it and subscribing. Thank you so much for doing that. Okay, let's move on to the third kind, electric field inside and outside spherical shells. This type has many different variations, so I'll touch on a few of them. Let's jump right into it. Given a spherical shell of radius small r, which is uniformly charged on the surface, find the electric field at distance x from the center of the spherical shell. If this is the shell of radius r and this is the charge on the surface, let's say our x is somewhere here. To find the electric field, first draw a spherical Gaussian surface at x. The object doesn't have length, so we're going to use spherical. Next, EA is equal to the charge enclosed over epsilon naught. Our area is the area of the spherical Gaussian surface, which is 4 pi x squared. But what is our charge enclosed? Notice the Gaussian surface does not enclose any charge, so our charge enclosed is 0. Therefore, electric field is also 0. If we are finding the field outside the spherical shell at distance big R, the charge on the surface would now be enclosed by our Gaussian surface. So EA is equal to charge enclosed over epsilon naught. A is the area of the spherical Gaussian surface, which is 4 pi big R squared, and Q is the charge enclosed on the surface of the spherical shell. We can then find electric field. So what if they didn't give us charge enclosed but surface charge density? Charge enclosed is the surface charge density times the area over which the charge is spread. The charge is on the sphere, not on our Gaussian surface, so it will be sigma times 4 pi small r squared over epsilon naught. Then E is equal to sigma times 4 pi small r squared over 4 pi big R squared epsilon naught. The 4 pi's cancel out. From there, you can find your electric field. So let's try a mutant example on this, because when you learn these, you can't fail no matter how much they twist the question. A uniformly charged solid spherical insulator has a radius of 0.23 meters. The total charge in the volume is 4 times 10 raised to the power minus 8 coulomb. Find the electric field at a point 0.14 from the center. So if this is the spherical insulator, the radius is 0.23 meters and we want to find the field at 0.14 from the center. We draw a spherical Gaussian surface there. EA is equal to charge enclosed over epsilon naught. A is the area of the spherical Gaussian surface, which is 4 pi small r square. They gave us the charge in the total volume, but we need to find the charge inside the Gaussian surface. So how do we do that? We have to find the volume charge density. Volume charge density is the total charge over the total volume of charge. If we multiply the volume charge density by the volume of our Gaussian surface, we'll get the charge enclosed by the Gaussian surface. So E times 4 pi 0.14 square is equal to 4 times 10 raised to the power minus 8 over 4 over 3 pi 0.23 cubed, that's the volume charge density, times 4 over 3 pi 0.14 cubed, that's the area of the Gaussian surface, all over epsilon naught. You can go ahead and solve it and you get 4138.6 Newton per coulomb. The very last Mutant problem we'll solve is a hollow conducting spherical shell, uncharged and charged, with a charge Q at the hollow center. So if this is an uncharged hollow conducting sphere, hollow meaning it has an empty space at the center with charge plus Q. This is region A, this is B, and this is C. If you want to find the electric field in A, you draw the spherical Gaussian surface there and follow the formula. EA is equal to charge enclosed over epsilon naught. A is the area of the Gaussian surface. Charge enclosed is the positive charge at the center plus Q. Substitute and you will get E. If you want to find the electric field in region B, that is inside the conducting shell, draw the Gaussian surface there and follow the formula. EA is equal to charge enclosed over epsilon naught, but you get the electric field as 0. Why? Because the positive charge at the center would attract an equal negative charge minus Q on the inner surface of the conducting shell. Charge enclosed is then plus Q minus Q, which is equal to 0. Therefore, the net charge enclosed by the Gaussian surface is 0 and the electric field is 0. In fact, the electric field in any uncharged conductor in electrostatics is always 0. For region C, draw your spherical Gaussian surface. EA is equal to charge enclosed over epsilon naught. A is the area of the spherical Gaussian surface. Now something important, we know that the plus Q here induces an equal negative charge minus Q on the inner surface, and this negative charge in turn induces a positive charge on the outer surface of the conducting shell. So the net charge enclosed is plus Q minus Q plus Q, which is equal to plus Q, and then you can find E from the formula. If the hollow conducting shell was charged with charge capital Q, then the total charge at region C would be plus small q minus small q plus small q plus capital Q. And then this over epsilon naught is equal to EA. Therefore, EA is equal to plus small q plus big Q over epsilon naught. That's all about applications of Gauss's law. I hope this was really helpful. Thank you so much for watching. Always keep learning and always leave a question to be answered in your heart. If you need to learn more about the introduction to Gauss's law, check out my previous video here.